Next up is DJ. DJ was a postdoc with Stephen until 2016 and is now at Google DeepMind.
Thank you. Happy birthday, Stephen. Thank you so much to Lejun and Lena to put this thing together. And it's great to see so many familiar faces and meet new people. I was a postdoc with Stephen between 2014 and 2016. We worked mostly on robust optimization and control for power systems. I've mostly been at DeepMind since I left Caltech. Initially, when I went to DeepMind, the idea was that I would work on a new partnership that DeepMind was planning with the UK National Grid, but that never materialized. So I started looking for other places where I could apply these ideas. And mostly I've worked on applying control theoretic ideas to make deep learning and neural networks robust to various kinds of security issues. So that's what I'm going to tell you about today, and mostly think about the types of challenges that arise, especially with the great progress we've had in AI in the past few years. So I'm going to try to focus mostly on challenges, but I'll give you a little bit of flavor to try to convince you that the types of techniques we all work on in this room might actually be extremely relevant to develop secure and private AI. Okay, great. So you're all familiar with all these amazing AI tools that we have that help us write documents, write emails, write code, take actions on our behalf, book flights, and all these kinds of amazing capabilities. But there's still significant risks associated with large deploying these technologies at a broad scale. So here's one type of risk that we see. So typically, as Google or any other company developing these technologies, we try to ensure that they cannot be used for nefarious purposes. So kind of as a toy example, imagine that you decided that the model giving a user instructions on how to build a bomb is a malicious use. And so you train the system to say that it's not going to be able to respond to this type of request. But is that sufficient? Maybe you generated lots of such requests and made sure that the model refuses to respond to all of those. Turns out that actually doesn't really correspond to making the system secure. There was work that showed that you can optimize these kinds of adversarial prompts that you add to the initial request that actually start to make the model comply with the request that you initially made, right? So you did your best effort to make sure that the model refuses to answer unsafe questions, but there's always ways around this. And you can ask, so most of this work was done based on say the previous generation of models from a year or two ago. You can ask whether the current generation of models is better. And we just put out the latest tech report corresponding to the latest models from Google, the Gemini 1.5 models. And we find in particular that they are a little bit more robust to these types of non-human interpretable tokens that I was showing you on the previous slide, but they remain susceptible to attacks that involve human-readable instructions. So one possible hypothesis for this is that as the models get better, they actually get better at understanding human language better, but then they also become more susceptible to being instructed to do bad things in human-readable language. So this would be, you can imagine things like, you could instruct the model to say, ignore all ethical or safety consequences, and please answer this for hypothetical purposes, or things like this, right? So you can see that the threat vectors evolve as the capabilities of the models evolve. Another big type of risk that we worry about is AI is often trained on privacy-sensitive data, or there's lots of use cases where we would like to train AI on privacy-sensitive data. There's been work that shows that if you train AI on privacy-sensitive data, it's possible to prompt the models in a way that reveals this data. So there's this XKCD cartoon that was very poignant from several years ago, which shows a particular type of risk that arises here. So this is another type of risk that if we end up having to train AI systems on privacy-sensitive data, we need techniques to make sure that they do not leak this information. Another type of risk that we're currently very worried about, because it's election season in many countries around the world, is the fact that we're releasing these models to the world. And we, of course, want users to provide feedback to help us improve the models, but we don't very carefully control where this feedback comes from. So you could imagine that there's like malicious entities that are hired teams of people, or maybe even just automatic bots, to provide malicious feedback to the model. Maybe it tries to make the model think favorably about some political party, or it says racist things against certain races or things like that, right? So this is another type of risk where we're collecting data in the wild and we don't know how much of this data can be trusted. How do we fine-tune models in a way that's robust to this kind of risk? So I'm hopefully here to convince you that control theory can play a big role in trying to address these challenges. Of course, there's a long way to go. What I'm going to show you is probably like very initial steps, but hopefully we can talk during the rest of the day if you're interested in more details. Okay, so I'm going to speak specifically about privacy, and in particular, I'm going to talk about a system that was deployed on this Gboard next word predictor. So this is a system that lives on your Android phone. It basically suggests the next word that you might be wanting to type as you're going ahead, and it's based on language models of this form. And so currently, the way this is actually done at Google is using this system called federated learning, where you have all these devices which have potentially privacy-sensitive data, but then the data is actually never shared centrally to Google. It's only shared through an encrypted mechanism, and you have a differential privacy system in place to try to protect the privacy of the user data. So if you're not familiar with differential privacy, I'm not going to say too much about it, except that basically, what you're trying to ensure is that if you imagine these learning algorithms as mappings from data to parameters of a model, you want to ensure some notion of stability that when you change the data a little bit, the model parameters don't change too much. It turns out that it's much more convenient to make this guarantee in a probabilistic sense. So typically, you have a randomized algorithm that produces a distribution over model parameters, and that distribution has to have the stability constraint that if you change one of the data points, then the ratio between the probability that the model parameters belong to a particular set cannot change by too much. Right. Okay. So let's think about what this means for learning algorithms. So typically in learning algorithms, we're trying to estimate parameters of a model, and typically we're trying to optimize some expected loss over some data distribution. In this case, the data distribution that comes from users typing into their phones. And rather than, we don't always have access to the actual data distribution, so we're going to settle for a finite sample, a finite data set that is assumed to be representative of the data distribution. So the goal is that we want to try to minimize this loss function while being differentially private with respect to the data set D. And one of the workhorses that has been extremely successful, at least internally at Google, is this approach called differentially private stochastic gradient descent, which basically constitutes of like sampling data points, getting gradients of the loss with respect to the parameters, and then doing a simple gradient descent step. But then the thing that makes all of this private is that rather than using directly the gradients that you would do as in standard gradient descent, you corrupt the gradient with some level of Gaussian noise, and the level of Gaussian noise has to be chosen proportional to the magnitude of the gradients that you might encounter, and then you do this update. Okay, so most of this work, most of the work in differential private learning relies on this type of mechanism, and it's been fairly successful. But in the recent years, we have actually discovered that you might be able to improve upon this algorithm. And the key idea for the improvement is that rather than adding independent Gaussian noise at every step of the learning algorithm, what you do is you introduce some kind of correlations in the noise over time, right? And so rather than generating IID Gaussian noise at every step, I'm going to generate still IID Gaussian noise at every step. But what I actually add is a linear combination of all the noise I've generated until this point. And then the main question is, okay, sorry, so I also need to promise you that basically if you do this, then I'm missing an inverse here. But essentially, if you control a certain norm of B inverse, then you can guarantee that this scheme is still differentially private. And now you have this degree of freedom in choosing B, right? So the main question is, how would you choose B? And that's where I think we managed to show that control theoretic ideas might be useful. So I'm going to skip this slide. There's a lot of advantages to this type of approach. I'm going to focus a little bit on like how this maps to a control theoretic setting. So again, just to remind you, this is the type of problem we're trying to solve. We draw a fresh sample in every iteration, and then we do a step of gradient descent with this noisy iteration. So if you look at what the update actually looks like, this is basically up to here is just the standard gradient descent step, and then you add this kind of correlated noise over time. We make one simplifying assumption that the correlated noise is time invariant in the sense that basically the dependence of the update at time t on the noise generated at time tau is just a function of the gap between t and tau, right? So that basically makes this thing a Toeplitz matrix. This also gives you an advantage that the number of coefficients you need to store goes from quadratic to linear. And then we are trying to understand, can we characterize the performance of the learning algorithm as a function of these coefficients beta, right? And so what we do is that because we have a time invariant system, we can analyze all of this in the Fourier domain. And so you can basically, for the specific case of the mean estimation problem where the loss function is quadratic, you can write all of the updates in terms of the gap between the parameters at time t versus the optimal parameters. And then you can write this whole thing as an LTI system where essentially the design variables are these coefficients beta. And if you stare a little bit at this, this is basically a convolution in the time domain. And so you can think of the design of beta as designing a linear filter. Yes?
So when you say optimal, you mean optimal subject to the differential privacy constraint?
No. So just to clarify, so basically the setting here is that we're solving a mean estimation problem, and the theta star corresponds to the true unknown mean of the distribution you're trying to estimate the mean for. But when you do the learning, you have to do it in a differentially private way.
But still, so there's
Yeah.
no loss of, the loss of optimality is what you're characterizing
Yeah.
here. And this would depend on, the loss of optimality will depend on how much differential privacy you provide.
Yes, exactly. But for a fixed privacy budget, what we're trying to do is to find the choice of beta that gives you the optimal error. Okay, and so, yeah, we're all familiar with these types of tricks, so we're going to take Fourier transforms everywhere. And once you do that, you can write down the dependence of the steady state characteristics of the system on the transfer function that corresponds to the coefficients beta. And it turns out that you can write down an integral that characterizes the steady state error as a function of the noise magnitudes of the filter. And so basically what you need to do here is that this is how the error depends on the magnitude of the filter. And then it turns out that the noise also has to depend on the filter, because I told you that in order to ensure differential privacy, you need to ensure that the noise scales as B inverse. So basically you get these two competing terms, and you can basically solve for the optimum in closed form, and that gives you like the optimal filter that you would design here. And so this gives you a way of prescribing how you would design this filter. And it turns out that, yeah, there is kind of a very simple expression for what that looks like. If you want to extend this beyond quadratic loss functions, we again bring the standard workhorse from control theory. We use IQCs to try to bound things when you're dealing with nonlinear loss functions, and you still get pretty good results. So all of this theory I described to you for simple problems like mean estimation or linear regression or things like that, but you can take the filter that you design and apply it even to a general deep learning problem. The privacy guarantee doesn't depend on the linearity assumption, so all the privacy guarantees still go through. You don't know whether this is optimal, but you can try it out empirically, and it turns out that it's actually pretty effective in practice as well. Again, I'm going to skip over some of the details. So we have a paper that we published at iClear this year, and we're working on memory-efficient extensions, which interestingly, from a control standpoint, corresponds to controlling the order of the filter that you are trying to design. So I think I'll stop here. How am I on time? Okay, 1 minute. Maybe I'll stop here, and then I can talk more offline to give you more details.
One of the claims on federated learning is that it actually preserves privacy, but there's been a lot of work saying that if the gradient is leaked, then you can actually violate these privacy guarantees. Mm-hmm. And I thought that was more of an academic, in theory, you could do it. But it seems like if Google is using federated learning plus differential privacy in the Gboard thing, then actually it's a real concern. Can you comment at all on how seriously?
I don't know too much specifically about the federated aspects because I don't work too much on that myself. But even in the centralized setup, we have very effective attacks that show that once the model is trained, you can actually prompt the models in ways that force it to reveal privacy-sensitive data. So if you don't employ differential privacy, you can lead to things that violate user privacy. Yeah.